Thanks, Alex. So this talk is called Accelerating Your VR Games with VRWorks. We're going to be talking about VR technologies that NVIDIA brings to the table and how game developers can take advantage of them to make their VR titles rock. So, and you've almost made it to the end of GDC, guys. Congratulations. You survived. I survived. Here's what we're going to be talking about today. So we're going to talk a little bit about sort of the underlying technology from NVIDIA, the Pascal architecture, the VRWorks SDK and platform. We're going to talk about the various VRWorks features. Some of them are newer, some of them we've been shipping for a couple of years. They're all kind of varying degrees of complexity, so we'll dive back in to sort of explain how those work from the ground up. Multi-res shading, lens match shading, single pass stereo VR SLI. We'll talk about some new stuff that we've got that has never been announced before in the form of a new API called SMP Assist that we're designing currently. We'll talk about some new extensions from Vulkan that enable a lot of this VR functionality on the Vulkan platform. And then we'll talk a little bit about VR tools. All right, let's get started then. So first I'm going to talk a little bit about the NVIDIA, where we fit into the VR ecosystem, what our platform for VR looks like. So we span sort of the entire gamut of functionality, as it were. So we've got obviously the underlying hardware that VR applications run on. We have an image here of a GTX 1080, which is sort of a high-end desktop class GeForce gaming GPU. But we have embedded devices from Tegra through high-end PC devices like a GeForce GPU, all the way up to Tesla devices in the data center for doing things like VR video processing or deep learning calculations for various applications, all of which potentially have VR ramifications and applications. On top of the hardware, we offer a number of SDKs and tools. So VRWorks is a combination of software and hardware, and it's more than just one SDK. It's a collection of SDKs that we offer, and we'll be talking about that primarily. But we also offer things like the PhysX SDK. So PhysX is our continuously improving and growing collection of physics simulation middleware, and a lot of that is generally applicable to games and 3D applications, but there's also specific VR-related applications there, and especially in the form of haptics and response to input and response to your surroundings that really makes sense in the VR context. And then we also offer tools. So Nsight, which is our sort of industry-leading tool for debugging and profiling, as well as FCAT VR, which is a great way to sort of determine the performance of your VR application. And then above that, we also offer applications, and we've been working on. We've been super excited about VR for a number of years now. So we shipped a couple of years ago the VR Funhouse game, which is that image at the top there. Let me see if this pointy thing works. There it is. This thing. I don't know if you guys have seen it, but you should check it out. It's available on Oculus and Vive, and it's basically a fun kind of a mini game where you get to play in this carnival, and it showcases a lot of our technology. It's actually a really fun game, but on top of being a fun game, it uses all the VRWorks technologies that we're going to talk about today. It uses physics simulation for hair and for cloth and fluids and smoke and things like that. And it uses a lot of the haptics functionality that physics brings to the table to provide haptic feedback through the VR controllers. And then this image right here is from Project Holodeck, which we announced recently, which is not a game per se, but it's definitely a VR application for mostly for design review type applications and collaborative VR experiences. What we demoed at where was it? GTC maybe or at CES. We demoed this tool where we were actually a number of designers were collaborating in the design of a vehicle. And they were in VR, interacting with it, making notes in VR to each other, sharing sort of, looking at different parts of the car and changing the colors and the materials and things like that. It's pretty cool. If we have time at the end, I'll show you guys a video of Holodeck because it's pretty fun, although it's not necessarily a game. First, I want to talk a little bit about the NVIDIA Pascal GPU architecture, which is the current high-end architecture that NVIDIA is shipping. It's obviously built on the latest transistor technology, 16nm FinFET, which gives you high performance, low power usage, and high sort of perf per watt and perf per dollar density. It's got the highest performance memory bandwidth through GDDR5X memories, which provides high bandwidth for high memory bandwidth, which is very important in VR. It sort of encapsulates what we call craftsmanship, which sounds like kind of a marketing-y term that everyone says about their products, but the reality is we actually do think this way, which is sort of not necessarily how do you design something to beat the competition, but instead how do you design the best possible thing? What is the actual, what is the speed of light, the perfect GPU you could build in terms of performance per dollar, performance per watt of power used, and we set that as the bar. And so every time we iterate on a GPU architecture, we keep improving the craftsmanship. And related to VR, we've got a number of new technologies. Simultaneous multi-projection is sort of the overall name that we have for that's sort of the underlying building blocks that a lot of our VRWorks technologies sit on top of, and we'll talk about that a lot today. And we also offer improvements to preemption. I'll talk a little bit about how preemption works and what the improvements are. So in previous GPUs that we've shipped, say the Maxwell family and before, we've always had the ability to preempt the GPU. Preemption just means sort of interrupting the GPU with other GPU work, right? So just like a CPU has to sort of task switch between different applications and different processing, a GPU also has that functionality. Historically, before the Pascal architecture, our preemption didn't work at a very fine granularity. It worked sort of at, you can say, like command granularity or draw call granularity, if you will. Which is fine for a lot of applications, but if you need really fast response and really fast latency, if you need to tell the GPU, stop what you're doing, do this other thing, there's latency there, right? You have to wait for those commands to drain. You have to wait for the commands to finish so that you can execute the new commands. So in the Pascal generation of chips, we actually drastically improved the granularity. Now, within a single triangle, we can actually preempt. So we can pause in the middle of a triangle, say, tell the GPU, stop what you're doing, switch to some new operation, and then go back to what you were doing. So the reason this is useful for VR is that VR, first of all, latency is just generally important. But there is this sort of interruption that happens in the form of time warp, asynchronous time warp, or asynchronous space warp operations where if the GPU is currently processing a frame, it'll get interrupted to do the space warp or time warp, which is a GPU operation, and then it needs to go back to what it's doing. So that's something that gets much better with the finer the granularity you have. Another thing that we've introduced in Pascal, which is the focus of much of this talk, is the simultaneous multi-projection architecture. So this is not only useful for VR, but it sort of has turned out that is the most useful place for this technology. What it is broadly is it allows you to do multiple different projections in a very efficient way on the GPU. So you can do lots of different things. Anytime you need to sort of render to multiple viewports, you can use this technology. This sort of shows kind of a surround gaming multi-monitor type of setup, it looks like, right? Where you've got different monitors with different projections into the scene, excuse me. So that can be accelerated by this technology. But VR is really a natural fit, right? VR has two projections naturally because of the two eyes. With some of these techniques we're going to talk about with multi-res shading and lens match shading, there's even more projections that need to be done. All of those can be accelerated by the ability that NVIDIA Pascal has to do multiple projections in a very efficient way. So I'll talk sort of briefly about the challenges of VR, what makes it unique, and which will give kind of the context for why it is that we've developed the technologies that we have. So the main one is basically that VR performance demands are pretty intense compared to your average game, right? Most games these days, 60 FIPS is like the gold standard, right? If you get 60 frames per second, you have a really smooth experience. Well, it's not good enough for VR, right? VR needs 90 frames per second. That's the refresh rate on most of the head-mounted displays, the HMDs. And you really need to hit it too. It's not only a higher frame rate, but it's also kind of a hard requirement that you hit that 90 FIPS. If you don't hit 90 FIPS, if you miss a frame, the penalty isn't just a tiny bit of stutter like it would be on a console or a PC game. It's a dramatically sort of uncomfortable situation for the user, right? And so there's a number of techniques that the HMD manufacturers have come up with to sort of minimize the costs of when you do miss a frame. But at the end of the day, missing a frame is is very painful in VR. And so you really need to hit 90 frames per second, right? So that gives you 11 milliseconds in a frame, which is not a lot of time. So you need a lot of a high frame rate. And sort of unfortunately, in addition to having high frame rate, there's also a ton of pixels that you have to render, right? if you look at something like the Steam survey, there's a large number of players on PC games today that render just at 1080p, even with really high-end graphics cards, right? They render still at 1920 by 1080. In VR, you have this sort of this display you see here takes into account the latest high-res headsets that were announced, like the Vive Pro, and it also takes into account the fact that some amount of super sampling has to be done to sort of get the image quality. We'll actually talk about that a little bit too, but the nature of VR rendering and the lens distortion means that all the HMD manufacturers currently do a little bit of recommend super sampling to be done to get high quality out of the final rendered result. And so that combined with a high resolution, combined with the fact that there are two eyes, means you're rendering a ton of pixels. So we're talking about, and then you have to do it at 90 FIPS, so you end up with like 800 million pixels per second or so is sort of the target for the number of pixels per second that your application needs to push. So that's pretty intense. And then on top of that, there's latency. Like latency is something which traditionally I think in gaming, basically if your frame rate was good, your latency was good. Like you didn't separately optimize for latency that much, at least on the rendering side. Like maybe input latency is something you would worry about. But in terms of rendering latency, you kind of just shot for, hey, if you got 60 frames per second, the latency is going to be pretty good, right? With VR, latency is sort of especially important. And because of that, some techniques which increase throughput, increase frame rate, but don't help latency as much, don't actually make a lot of sense in VR. And so you have to be kind of cognizant of this. There are things we've done in the past and everyone has done in the past where it improves the frame rate but doesn't improve the latency of the application. That kind of stuff doesn't work well with VR, so you can't use those kinds of tricks. So all this combines to mean you need a lot of performance. Here's sort of a diagram of sort of a 3D renderer, if you will, or just sort of a generic game system. In this one, we're doing deferred shading, or something approximately like deferred shading. So you've got sort of the inputs into the game system, general assets. You've got some sort of simulation that happens, which takes in user input, and then it does the renderer, right? These boxes are not necessarily to scale, Actually, as you'll see in the next slide, they're really not to scale. But basically, there's some amount of sort of view-independent stuff that happens. There's general rasterization that happens. There's shading that happens after that, probably, because you're doing deferred shading, which is fairly common. Then a bunch of post effects that happen, right? So this is fairly common sort of setup. And VR, can work exactly like this too, more or less, modulo some user input and stuff like that. But typically what we've seen is that it looks a little bit more like this, where we have some additional boxes in the form of things like time warp and lens distortion that has to happen now, different inputs that happen from the HMD, different inputs that happen at different parts of the pipeline. And what we've seen in many applications is that deferred shading, for a variety of reasons, is not the rendering paradigm of choice for VR. It comes down to a few things. Number one is mostly performance. Number two is probably wanting to be able to use techniques like multi-sample anti-aliasing, which doesn't work well with deferred shading. So a lot of applications do forward shading instead, and then do sort of a minor amount of post-processing, and then do these other not-to-scale boxes here that take into account the special characteristics of VR rendering. So we'll talk a little bit about those. So there's this idea of time warp, which I'll talk about the simple version of that a little bit. There's a more complex version of that called space warp, which people have been shipping now. But what it basically does, and most of you probably already know this, so I won't go into this too much detail, but it just allows you to lower the latency, right? Instead of just sampling the head pose, submitting to the GPU, and then flashing the backlight to after scan out so the user actually sees it, we instead introduce an additional head pose sampling at the end of the GPU rendering. And then what happens is that a little post-processing shader gets run to do a warp based on that new head pose, and that new slightly warped image, hopefully slightly warped, the more it warps, the less good it looks. Slightly warped image is sent to display, which gives you lower latency, basically, right? The user has responded, has moved their heads, and that movement is reflected in the image they see. What that helps you with is a scenario like this. Actually, this scenario is pretty nasty. Not much that can help you here. But what you end up having is, you have this sort of frame, and then you do a little warp, and you display the frame 1 with the warp 1. And then you have this really horrible frame, which is like 3 times as long as frame 1. And you're in trouble here, right? So what we can do is we can do a warp 2. This is, we're talking about time warp here, but this is, on modern systems, probably a asynchronous space warp operation, which does a more sophisticated sort of resampling of the scene, and then it displays that frame one with that sort of synthesized space warp / time warped image. So you don't have a completely dropped frame, which is what you would have here. Right? If you had a completely dropped frame, you would basically display the same frame one identically, and then it would be extremely stuttery and not a great experience. This also highlights sort of the preemption thing I was talking about previously. These warp operations have to run on the GPU, just like this rendering has to run on the GPU. And so this warp operation has to sort of interrupt this frame 2 rendering and say, hey, okay, hold on. Sorry, we're about to miss. We got to do this warp on the GPU so that we have something new to display that doesn't look exactly like the previous frame, which is going to feel like extremely high latency and a drop frame to the user. So that interruption and preemption and issuing of the warp and then getting back to rendering frame 2 has to happen very quickly. And the quicker that happens, the better the experience for the end user. Okay, and then the other sort of quality of VR rendering is the fact that there's a lens distortion, which we all know. This is because there's optics in the actual device itself to allow you to focus on a display that's very close to your face. And so what that means is that the actual image sitting in the frame buffer of the display of the device has to look, like this, right? And GPUs can't actually render in this sort of weird space, so we have to do a bunch of tricks to get the image into this sort of a space, so that when the optics are applied, just like the physical optics that are applied by the lens that's physically on the device, what the user actually sees, in their retina is something that looks like a normal rectilinear projection, right? So this has some qualities to it, and it can modify some of the trade-offs and optimization opportunities that exist in VR. Okay, so now I'll talk a little bit about our VRWorks and how it relates to all those challenges and what it addresses. This is sort of the current VRWorks suite. We're not going to talk about all of these today, partially because we don't have time and partially because some of them aren't really that relevant for game developers. The leftmost column there, the graphics column, is the most relevant to game developers, so we'll talk about that for sure. Some of these other ones are also relevant, but it's not really the focus of this talk. Certainly, physics is an entire set of talks in and of itself. That gives you physics simulation and things like haptics. We have the VRWorks audio. That's currently released, and it has a UE4 integration. If you're interested in checking that out on our website, it's linked off the main VRWorks site. That gives you sort of positional immersive audio that works really well for VR applications and uses actually ray tracing to simulate the way that audio waves propagate through a surface and handles occlusion and things like that. It's very cool. And then we have some sort of professional and video processing SDKs that allow you to do things for non-interactive, more video and streaming types of applications. And these headset ones are mostly for the headset manufacturers, guys like Oculus and Vive. We're going to be talking about the graphics features today primarily. So I've sort of broadly bucketed the things into two buckets here. There's a set of technologies that we have that mostly focusing on rendering less pixels. With the idea that the less pixels you render, the less you shade, the faster your application will go. Right? That's multi-resolution shading and lens match shading. And then there are some that allow you to sort of render richer, more detailed scenes. They accelerate either the geometry part of the pipeline in the case of single pass stereo, or the entire pipeline in the case of VRSLI. Right? And so they sort of attack different parts of the pipeline and different parts of the optimization problem, and sort of work in concert to accelerate your application. We'll talk about the rendering less pixels part first. And this is sort of the more complex part, and I think the more confusing part. So we'll spend a little bit of time on this. So again, to review, we sort of have this optical characteristic that all VR applications have, right? Where the actual data in the LCD display is this warped data. And then the photons go through this optical lens that the device has, and then the user actually sees something that looks normal. And so we got to get the thing that we render into this sort of we need to make it look like this, right? And so in modern VR systems, that's handled by the VR runtime. It's not something that your application typically has to worry about. And the way that works is that we have, your application actually just renders a normal, plain and simple sort of rectilinear projection as you always would. You don't have to worry about this. And then you hand your surface to the runtime. The runtime does this warping operation. That's a warp that takes into account the characteristics of the lens that the lens manufacturer knows about, and applies the correct distortions so that when the user actually sees the image, it looks correct, right? So one thing to notice right off the bat, right, is that this is like way less pixels than this, right? So we have a lot of compression that's going on here, and you end up essentially throwing away, or mostly throwing away, a lot of the data that's in the periphery, which is a real shame, right? We have all this really hard limits from 90 frames per second and super high resolution, and yet you're also kind of doing work that you don't need to. So the techniques we're going to talk about here address and try to overcome that sort of limitation, or overcome that unnecessary burden of rendering extra pixels. So here's another sort of visualization of what it could look like, where we have this red rectangle on the left there. You see that after the warp, it gets warped into and bent into something which is far smaller in terms of number of pixels covered than the original rectangle, right? And so you've sort of over-rendered in the periphery there, basically. That's another way of saying that. And then you look at the ellipse that's in the center, though, it hasn't changed in size. And so what you would ideally like to do is some sort of rendering technique that allows you to render at varying resolutions throughout the frame, right? Which is not typically the way that rendering works. Typically, we have sort of a fixed resolution. So the challenge was, how do we do varying resolution rendering where we can maintain the quality in the center of the image, because those pixels really matter to the end user in VR, but reduce the rendering in the periphery where a lot of that data gets thrown away anyway, right? So the first technique we came up with was called multi-ray shading. And the way this worked basically is dividing the screen into a number of viewports, which here we've picked 9. You can pick sort of any number. Well, not any number, but you can pick not 9. But we found that 9 works well. It works well with sort of odd numbers because you want one viewport in the center. And then what you do is you scale the viewports differently. And what that means is that basically, sort of the ratio of pixels to, say, inches on the screen, the physical space is different in the different viewports. And that's totally up to you to set. And you can set that however you want. And what you have is you have a center viewport that's the same size, approximately, say, it's up to you, which maintains the resolution. And then the peripheral viewports, in this example, we have sort of half scaling and quarter scaling, but you can do it however you want, like I said, render at lower resolutions. And so what you end up doing is you end up having this rendered image which looks like this, and also the projections are just kind of strange, so it will have to end up getting stretched back out before you submit it to the runtime. But what you've done is in the periphery you've shaded and paid the memory bandwidth cost and all that stuff for far fewer pixels than you would have originally. And that's totally fine from an image quality standpoint because those peripheral regions are getting squished down by the lens distortion anyway. So for this to work, you need a bunch of things. You need graphics hardware that can render to multiple viewports simultaneously, which we've had for a few years now, but it's a relatively new feature. You need to be able to route geometry to specific viewports, which we can do in modern graphics APIs as well. So you can decide, this triangle, which viewport does it go to? It could be one, it could be none, it could be multiple viewports if it spans viewports. So you need that functionality. So you can do that through the geometry shader in modern graphics APIs. And so that's what we sort of settled on. Hey, this is cool. We can divide the screen into these sort of unequally sized viewports. We can submit the geometry. We can have a geometry shader that decides which viewport to route each triangle into. This is going to be awesome. We'll save a lot of rendering. Well, one of the problems is, if any of you have ever used a geometry shader application, is that geometry shaders have a performance cost just sort of by turning on geometry shaders. And it's not severe, but it exists on all hardware. And the whole point of this exercise is to optimize your game and make it run faster, right? And my least favorite form of optimization trick is one where it sort of helps in some cases and hurts in others, right? That's really not fun because then you can't just turn it on all the time, right? And then you have to make sort of content-specific or level-specific or rendering path-specific decisions on whether or not you can turn the feature on, and it becomes like this complete complex thing. Because in some cases it might slow it down because you're using this geometry shader part of the pipeline that can have a performance hit. And in other cases, it would be a speed up. So it just becomes more challenging to integrate. So what we did is we came up with this thing, which is this new optimized sort of path through the hardware, which is part of this simultaneous multi-projection architecture that I talked about, which we call fast geometry shader. Which what it allows you to do is basically have a piece of geometry and coming in, a triangle coming in, and then you can broadcast it to any number of viewports, to 0 to n, where n is the number of viewports bound. And if your geometry shader is sort of specially written in that way, where it doesn't do anything else, it just does this routing, and maybe like a little bit of culling, but there's sort of very specific rules as to what it can and can't do. And we have sample code and on our website that shows how to do this, and we have our integrations into the major engines which shows how to do this. But you have to be careful, right? The whole point of this is that if you follow all the rules and you don't do anything more than just doing routing, it'll be a special fast path through the hardware that allows you to not pay any penalty for using geometry shaders. And so you get that same sort of throughput that you would get even if you weren't using geometry shaders, because you're using this special subset geometry shader that we call fast geometry shader. So what this enables you to do is turn on something like multi-resolution shading all the time and be confident that it's not going to slow your app down, and it's only going to be a speed up in all the cases where pixels are your bottleneck, right? Okay, so that's multi-resolution shading. So then the Pascal generation, which is the current sort of high-end GPU that we're shipping, we improved upon this with something we call lens match shading. So this is a refinement of multi-resolution shading. You can think of multi-resolution shading as being basically trying to match the shading rate that you're doing when you're shading your engine, your game, to more closely match what the end user is actually going to end up seeing, right? So you want to match your shading rate to the lens characteristics. You want to do less shading in the parts that the lens throws away a lot of the data. You want to do more in the parts that require more. So multi-resolution shading does that too, but as we saw, there's sort of this discrete transition, right? You have a center region that has a certain shading rate, and then you have a viewport that has a very different shading rate. And there's a discrete transition between those two. Whereas the lens doesn't work that way, right? The lens has sort of a curvature to it that smoothly drops off as you go to the edges. But it doesn't capture that with multi-resolution shading. You just have to pick sort of a conservative fixed ratio of pixels and go with that. So it was a little coarse and suboptimal, so we came up with this improved implementation in the Pascal family, which allows you to better match the actual characteristics of the lens, better match your shading rate to the characteristics of the lens. This is what it ends up looking like. It also relies on this fast geometry shader that I talked about, because it does also divide the screen into multiple viewports. In this case, though, it's 4. And what it basically does is it has 4 different projections using the simultaneous multi-projection architecture of Pascal, which have different characteristics. So they actually are not fixed difference in shading rate like we have with multi-resolution shading, but instead a smoothly varying shading rate as you go to the corners. So it actually changes the projections completely in these 4 quadrants and ends up generating this sort of strange-looking octagon in your frame buffer, where the center has a high shading rate, has all the pixels you'd expect, and then it smoothly drops off as you get to the corners. So I'll talk a little bit about how that looks. So you have, here's sort of an image with the standard rendering on the left, and then here's one of the warps that you apply for the upper left quadrant using these warp parameters that lens match shading uses. And these are all flexible. What degree of fall off you can have here and stuff like that is all up to the game. We have some recommended settings and some presets that we offer. But as you can see by the nature of this projection, you have sort of, this is sort of the center of projection, and then it falls off towards the edges. So here you have less pixels, less shading rate per sort of inch of screen real estate, and here you have more, and it's a smooth sort of transition, right? But this only sort of makes sense for this corner, right? Because we want it to smoothly fall off towards the edges. We don't want this part. This part is all wrong, right? This doesn't correspond to the lens at all, but this does. So we basically scissor off this part, and this ends up being rendering 1. And then we do the other one with a different projection. This is for the upper right quadrant. Similar idea here. It's not a perfect mirror of this because the lenses are not perfectly symmetrical. So it matches the lens characteristics. And so you change these warp parameters actually from device to device potentially. So this is for this quadrant, and we scissor that one off, and that ends up being the upper right. Similarly for the lower left, and then as you would expect for the lower right. So you have these 4 different projections, 4 different scissored off sub-renderings of this image that correspond to those 4 projections, and then you combine those 4 into one image in the back buffer, and that's what your final rendered surface looks like. Now, the runtime expects sort of a normal looking image. It doesn't expect this strange octagon thing. So then you do have to do a post-process pass over that to sort of flatten it back out, right? Just to give you a normal rectangle to hand to the runtime. And what that flattened out image will look like basically is that you'll have less detail in the corners. It'll be kind of softer because you're stretching these pixels out, and you'll have sharpness in the center. But that doesn't really matter because that's all going to get squeezed down by the lens distortion done inside the VR runtime anyway, right? So this works really great, and we're super excited about it. This is kind of an interesting visualization that shows the various, at least potential speedups and the pixel rate savings that you get from using this feature. So over here we have kind of the baseline, what that means is what you do. Let's say you're running on a Vive, what it does without any lens match shading or multi-resolution shading. So what the colors mean here is undersampling is red and oversampling is blue. What undersampling means is that you're sampling less than once per pixel that the user sees. What oversampling means is that you're sampling more. So we talked earlier about how you're sort of over-rendering in the periphery, right? And so you definitely see that with this visualization, right? With the standard parameters that you use for a standard VR application, the perimeter is super blue, so you're massively overshading here. And actually, the center is slightly undersampled, which is okay, because, I mean, this shows red here, so you think, oh my god, it's undersampling, it's going to look bad. It doesn't. It's slightly softer than ideal. And that's just because the lens distortion sort of distorts out the center a little bit. And this is one thing this is why all the modern headsets do a little bit of super sampling. This is after super sampling. Without super sampling, it would be a lot redder. But it doesn't. They all do a little bit of super sampling because otherwise you get a very soft center, and you don't want a soft center. But anyway, so this is what it starts with. A little bit undersampling in the center, and then a lot of oversampling in the corners. And then you can see sort of these are 3 presets that we offer in our SDK, and they're integrated in the game engines that we offer integrations for as well. The first one we call quality, which is a neat preset because what it does is basically no undersampling. So this is higher quality than the actual default settings, right? So despite the fact that, so you see here's the number of pixels, 2.54 million pixels per eye is what you get for baseline. So this is quite a bit less, and it's actually higher quality than you get with the baseline because you have no undersampling at all. Right? So this is the lens match shading case up here. This is the multi-resolution shading. So you can see that sort of harsh transition, like I talked about, this discrete shading rate transition. So this is what it looks like. So what you end up having is if you want to guarantee no undersampling, multi-resolution shading will use more pixels. It's less optimal than lens match shading, which is sort of what you'd expect, right? Like we talked about, lens match shading is it's a better fit for the actual lens characteristics than multi-resolution shading is, right? So, so as you go to the right, in terms of columns to the right, we have the next one, which is the conservative one. This is another preset we offer. So what this says is basically we're not going to do any worse in terms of undersampling than what the default that you get from, say, a Vive, right? So there is some undersampling even there, like we said. And so this also says, okay, I'm going to do an equivalent sort of amount of undersampling. And what is the amount of pixels that you'd need to get that? So as you can see, that's a dramatic, it's less than half. And you have the same quality as the baseline with less than half the pixels. So that's pretty awesome, and slightly more than half in the case of multi-resolution shading. So this is very exciting. And actually, with lens match shading has this other cool characteristic that not only is this no worse, I would argue it's actually slightly better, because the places where you undersample are not the center of the image, which is kind of the place that the user will look in. Especially in VR, I think people don't, instead of turning their eyes around, I kind of tend to move my head in a VR application when I want to look this way. And so you tend to sort of look in the center of the image. And the center of the image is less red. What that means is it has a higher sampling rate. So you don't have undersampling in the middle of the image. So it's actually, I would argue, slightly higher quality than the baseline. And then we have this aggressive preset, which does more undersampling. This looks really dramatic. You're like, oh my god, this is going to look terrible. There's so much red. Red is bad, right, Jem? Yeah, a little bit. But the reality is that in a real game, most people, this is the common one that people pick. And the reason is because, yeah, you get a little bit of softening in the periphery. Especially with lens match shading, like I said, you still have this nice behavior where the center of the image is sharper than the periphery. So it's hard to really see that, and it's a dramatic savings, right? You're talking about less than one megapixel per eye compared to 2.54 is where we started. That's pretty awesome. We've actually had developers, because this is all flexible, you can set these to whatever you want. We've had developers go even more aggressive than this. They're like, this isn't aggressive enough. I can't see the difference at all, even with this. Let's jack it up even more to get even more performance. So I actually don't think that aggressive is super aggressive. I think it's actually pretty pretty exciting and common. The most common one I think to use would be the aggressive preset. Okay. Here's a video in Unreal Engine 4. Show you guys how this looks. So it starts with sort of the baseline. This is just normal rendering, and then it applies the lens distortion. There's the lens distortion. So you'll see right away that the center got softer. Even in this video, this compressed video that we have here, right, you see that the center got softer for sure. It's blurrier than it was before lens distortion gets applied. And this is why the super sampling is done. So this is going to show sort of pre-super sampling. It looks like this. And so you get a lot of undersampling. You get a lot of red. Red is bad, remember. Blue is also bad, you would argue. But red means sort of blurry. So then they turn on the super sampling feature, which everyone recommends. So you have less red. So that's getting better. And now we're going to show sort of the lens match shading quality preset. I can pause it here for a second. This is, so you see it's just sort of very slightly blue. I can go back and show you what it was like before. Right, this is sort of a lot of blue in the periphery, but also some red. This is the standard. I believe this was taken on a Vive. This is sort of the standard for a Vive. Lens match shading quality looks like this. So much less red, so higher quality, sharper in the center. And if you actually look at the image, it actually does look sharper in the center. Even in the video, you can see the sharpness increase. And then if I let this video run, it goes through a bunch of the presets here. So this is the quality for lens match shading. Then we've got quality for multi-resolution shading. Then we're going to flip from this into the conservative for lens match shading. That's what that is, conservative for multi-resolution shading. And then the final one, which is the aggressive. So I can pause it here. This is the aggressive. I don't know if we have, let me see, can we see it before it? Not really. So you have to look through the colors here to see the sharpness. But as you can see, it's not like a blurry mess, right? It still looks pretty sharp, the underlying geometry here, even with the most aggressive preset that we offer. And this is aggressive for multi-resolution shading, which has sort of very strange characteristics, as you can see, in terms of shading rate. It goes from high to low to high to low as you cross these multi-resolution shading boundaries for the viewports. Okay, cool. Let's see if my clicker still works. It does. All right, so there's a few challenges with these techniques. They're really cool, very exciting, and but what has been getting in the way of these getting adopted everywhere? All right, it's a couple of things. So the first one, which is pretty minor, is that there is this sort of, when you're done with multi-resolution or with lens match shading, you have this sort of strangely warped buffer. Now you have to apply an unwarp operation to that buffer to get it back into the correct sort of rectilinear-ish projection that the runtime, the VR runtime actually demands, right? So you have to do this resampling to hand it to the runtime so that the runtime can just go and then do another resampling to get it back into the lens distorted space. It's kind of a waste. It's extra shaders and stuff that you have to have in your application to do that. It's a little bit of extra code, and it's a little bit of performance loss because there's a pass that's done over your frame buffer, and it's a little bit of a quality loss because there's 2 levels of resampling or an extra level of resampling. Not a big deal, honestly, but it's a little bit of a challenge. And then the much bigger challenge, which we've been sort of working on for a while, is the fact that there are application changes. It sort of depends on how complex your application is, but for the most complex of applications, it can be a lot of work to integrate these features. And the reason is because, like I said, it relies on geometry shaders. So if your application needs to create these new geometry shaders, it needs to make sure that they're fast geometry shaders, that they're created in the correct way. And if your application didn't previously have support for geometry shaders, you have to sort of add a new shader type and things like that. So it's a little bit of a burden for this one feature. There's state that needs to be set in the form of viewport, scissor state, to set it up for the individual viewports. And then there's also potentially a lot of shader changes. It depends on the type of rendering effects your game has. You know, if your game is sort of forward rendered, not a lot of complicated post-processing, then this actually is not a huge deal. There's a couple of little things that you have to change, but it ends up being not a problem. At the other extreme would be a fully deferred shading engine that has tons of post effects, which do all kinds of crazy coordinate space calculations and mappings and remappings and stuff. Those become challenging because now you've sort of warped the coordinate space of what screen space means. And so now you have to take that into account. So your shader that previously was kind of dumb about it and assumed that a certain mapping, a normal mapping of screen space to say normalized device coordinate space, now it's potentially different depending on where you are on the screen, right, in the case of multi-resolution shading. If you're in one of the corner viewports, you have a different mapping versus the center one. And with lens mask shading, depending on what quadrant you're in, it's a different warp function, and you have to do this math and stuff. Now, we have the code for all that available, but it does require the person writing that shader to think about that issue. So it can be a bit of a burden there. But like I said, that's mostly a function of that's hardest for deferred shading engines. For forward shading, it's not a big deal. So one thing I want to talk about a little bit today is SMP Assist, which is this new feature that's not quite available yet, but will be available soon from us, which will help with some of these issues. So first, on the unwarping issue that I talked about, this was really cool. So Oculus recently shipped in one of their recent SDKs a native lens match shading enabled compositor in their runtime. So what that means basically is that instead of having to do all that unwarping in your own application, when you're done rendering into that LMS surface, which means you have this sort of octagon result in your back buffer, you just hand that directly to the Oculus runtime. You don't have to do any unwarping, so there's not resampling that has to be done. And then the Oculus runtime itself just directly turns that into the lens distorted, the pre-lens distorted result that the optics need, right? So it saves you a step in the application. It saves a resampling and shading and pass over your frame buffer. So it's a little bit faster, a little bit higher quality, and so it's a win-win, right? No downsides at all to this. So this is cool. This is now available in the latest Oculus SDK. And then the other thing that I want to talk about today is SMP Assist, which we've never talked about publicly before. This is sort of hot off the presses, if you will. It's something we're working really hard on right now, but it will make it available pretty soon. So the way this works basically is it doesn't solve the whole problem, but it does solve the creating shaders and setting state. It helps a lot with that part of the problem, right? So this is something that developers have been telling us for the last couple of years, that we've had features like this where they said, hey, is there anything you can do to lower the implementation burden? So this is our first attempt at that, where the responsibilities, which previously were entirely on the application to handle all this stuff, now there's sort of a split. There's some things you have to do. So in this case, you have to do this. You have to create an SMP Assist interface, set up your projections, how you want to do them. And then all you have to do then is just enable SMP Assist and disable SMP Assist around the rendering calls that you want it enabled on. And what that does is it will automatically, at creation time, it will automatically create the appropriate geometry shaders. It'll make sure that they're actually fast geometry shaders so that they abide by all the rules that are necessary to get that fast throughput that we offer. And then it will also handle binding those geometry shaders, unbinding them, setting them the state that you need viewports and scissors correctly for multi-resolution shading versus lens match shading, depending on which technique you're using. Set the parameters correctly for the device that you've said you're running on, so the lens parameters are set correctly. Basically, it'll handle everything it can, right? It'll then return some constant buffer data, or in a constant buffer, it'll return data which tells you sort of the characteristics of what it did in case you need that, say to modify a shader, or you need that to do the unwarp. Let's say you're not running on the latest Oculus thing, or you need it for other devices where you need to do the unwarping yourself. You need to know the lens match shading parameters and stuff to be able to do that unwarping, right? So it'll provide that information back to you depending on what it created. But during the running of the game and rendering, you don't have to worry about any of the geometry shader creation or binding or state creation or binding. All that stuff will be taken care of for you. We offer a few different sort of levels of SMP Assist in the current sort of prototype that we're working on, which range from full, where it will do everything it can, which basically means you just say, hey, I'm running on this device and I want this level of quality, and then all the parameters will be sort of created for you. You won't even know how it works necessarily. The shaders will all get created for you, and the state will be set for you, etc. To partial, where you can sort of set the MRS and LMS configs to your liking. If you have different settings that you want to use instead of the presets that we have, the aggressive, the conservative, and the quality, if you want your own sort of config, which a lot of developers have wanted, you can set the parameters yourself. But then partial is really close to full. It still does everything else for you in terms of geometry shaders and state. And then there's this sort of minimal for the case where you need to set your own geometry shaders or something. You need to do something very customized and in terms of the parameters for lens match shading. So this is almost no different than what you have without SMP Assist, except that some of the state will be set for you automatically, so at least you don't have to worry about that. So this is SMP Assist. Like I said, this is coming soon from us. I'm excited about it. I expect it to help with the implementation burden and help with adoption. Okay. So this is the part of the problem that we don't help with, sadly. We've brainstormed about it a lot, and we don't have a generic solution to this. So we don't have to go into the gory details of this code snippet here, but the basic idea is you see this code here. This is the problem I was mentioning, where it's a deferred shading shader here. This is a directional lighting shader, pixel shader, and this is the challenging case where you have deferred shading shaders. Typically, they have to sort of take something from screen space back into world space or some other canonical space in which to do the mathematics for the lighting, right? And so what you have here is that you have this SV position, which is sort of the screen position that's provided by the API. Am I still mic'd? Yes. And what we have to do is you have to basically, if VR is on, you have to linearize that, right? It's in this LMS space, this lens match shading space. We have to convert it, in the case of VR projection on, to a linearized thing so that we can actually do this sort of, here we're going to do this mathematics with some other data, and that camera vector, where is the camera vector, is not going to actually work. It's in a different coordinate space than, right here is the camera vector. It's in a different coordinate space than LMS space. And so you have to put them both in the correct coordinate space so that the linear algebra makes sense, right? So, and this is a particularly annoying example because right here you've got a screen space thing that needs to be unwarped using this operation. And then right down here you've got UVs, which are also in LMS space, but they should not be unwarped. And the reason is because when you're doing like fetching from a G buffer in deferred shading, you actually want to fetch from the current pixel you're at. You don't want to change it based on the MRS or LMS parameters. You need the pixel that you're currently shading to fetch the G buffer parameters. And so you sort of have to know the algorithm, which is irritating, and which is why you can't just come up with sort of a generic solution that works for all cases. You have to actually understand that this one needs to be transformed and this one doesn't. So, like I said, in the deferred shading case, this is a challenge. In the non-deferred shading case, you have much less of these sort of coordinate space transforms. If you're just doing forward shading and you're just shading as you go, the math works out, and so you don't have to change most of those shaders. So it's easier, but this case remains a challenge. So quickly, we also have this sort of rendering larger scenes, we call it, subset of features. And they rely on a couple of things. One is that we have this characteristic of VR where you're doing stereo rendering, right? You have two eyes, left and a right, and they're very, very similar views of the scene, but you have to do two full re-renderings of all your geometry and go through all your entire scene for each eye, which seems kind of wasteful. And so as part of this simultaneous multi-projection architecture in the Pascal generation, what we came up with is this thing we call single pass stereo. So this is in some ways similar to instance stereo, which a lot of applications do now, but it's sort of a superset of instance stereo. It's better than instance stereo because what instance stereo does is it basically cuts down on the CPU cost of submitting your scene twice, once for each eye. Right? What single pass stereo does is it cuts down on that cost as well, but it also cuts down on all the front-end geometry processing that an application, that the GPU has to do as well. So it's actually a real hardware feature in addition to a software feature, where the hardware will actually keep only one, like you only have to do vertex processing one time for the vertices in both eyes, for example. You only have to do things like pulling in attributes for vertex data one time instead of two times. So in addition to helping with the CPU cost, because you only have to submit your geometry once, you also only have to process your geometry once. And it has good synergy with lens match shading, where lens match shading cuts down on the number of pixels you have to render. This cuts down on the amount of geometry you have to process and CPU cost as well. And so it sort of optimizes both parts of the pipeline. The other feature, which I've talked about before, I'm not going to go into too much detail here, but it's VRSLI, and it works the way you'd expect, which is 1 GPU per eye. And that ends up, and then we have a number of APIs through all the major APIs, for Vulkan and DirectX to be able to decide, what rendering goes to which eye, which rendering goes to both eyes. Because some things that are view independent, you need to send to both eyes or do a copy between the eyes, up to you. But we provide APIs for all that stuff as well. So this is why we do VRSLI the way we do it. This is sort of, if you fire up a game on an SLI rig and a PC SLI rig today, non-VR game, this is the way we do SLI typically, which is where we have, 1 GPU, the CPU submits 1 frame N, GPU 0 renders that frame N, and then when that's done, you see this line right here, it gets displayed. Similarly, N+1 gets submitted, etc. So this is called alternate frame rendering, and this is the way we've been doing SLI for a long time. But the problem, and let me go back real quick, the problem here is that if you look at the actual, what is the latency if I didn't have 2 GPUs? You look at this line, it's actually the same as it would be if we had only 1 GPU, right? It doesn't help with latency at all. It just helps with throughput, helps with frame rate. So VRSLI helps both with latency and with throughput. So here what we have is we submit once, it gets broken into the constituent left and right eye renderings, which are very similar, so they share a lot. And then they're just displayed once on the display. And so the latency is also improved in addition to the throughput. Okay, here's some sort of speed ups. This all depends on your application, where the bottlenecks are, which VRWorks features are used. But these are real shipping applications that have been sped up, anywhere from 20% to 80% using combination of VRWorks features. So that's pretty cool. I think most of these are Unreal Engine titles. Graphics support for the VRWorks graphics features. I'll talk a little bit about engine support and then API support. On the API side, we support all the APIs basically. DirectX, of course, DirectX 11, DirectX 12 as well. Some of the stuff like VRSLI and DX12, you need to code it yourself basically. There isn't, that's the DX12 model, right? You have explicit multi-GPU. We have OpenGL support. And I'll talk a little bit about the Vulkan support because that's very new. On the engine side, we have and have had Unreal Engine integrations of various VRWorks features. At this point, we have all of them available in the latest, which is almost the latest. I know Epic released 4.19 this week. That's coming soon. But one thing actually for Unreal Engine developers out there, a thing that Epic did in the last year is that they introduced this new VR optimized forward renderer. So currently, our integration supports both that forward renderer and the traditional deferred renderer, because we've been doing these for a while. As I mentioned before, a lot of the challenges in VR with VRWorks integration come from deferred renderer issues. So if people tell us that the deferred renderer is not useful in VRWorks Unreal Engine, and we should just focus on the forward renderer because that's what every VR game uses, if that's true, I don't know that's true, then we would love to do that because it would be, we'd be able to turn them out much quicker, and it would be much more efficient to do so. Currently, what we're doing is we support both of those renderers entirely with all the features that we have. Similarly, for Unity, we've been shipping this as well since 2017.1. It's a plugin for Unity, which is nice, so it's easier to take as an integration compared to the Unreal Engine integration, which is an engine integration. Supports all the features that I talked about today. And it, for similar reasons, supports the forward renderer, right? The similar reasons I talked about with the challenges with deferred renderer. Now, I think most Unity titles do use the forward renderer, so I have not heard this being a major problem. If you want to learn more about our Unity integration, we have this great sort of getting started web page, which will walk you through how to install the plugin and how to use it and stuff like that. Okay. On the Vulkan side, because Vulkan is neat and new and exciting, we do now have support for all of these features. So we have the multi-resolution shading. We have NVIDIA extensions for submitting geometry to multiple viewports and for doing the fast geometry shader work that's needed for multi-resolution shading. We have lens match shading as well. We call it clip space W scaling because that's actually how lens match shading works. It modifies the clip space W of the geometry. And then we have single pass stereo extensions as well. And as of I think last week, Vulkan 1.1 came out, or maybe the week before. It introduced multi-GPU sort of natively into the Vulkan API. And this can be used, this is similar to what I was saying about DX12, it's explicit. We have an MV API for older APIs like DX11. For modern APIs like Vulkan or DX12, you sort of program the multi-GPU stuff yourself. So if you want to do something like what I talked about, VRSLI, 1 GPU per eye, that's up to you to program. And now in Vulkan 1.1, there is support for having your command buffers go to specific GPUs, or having subsets of those commands that are subsets of command buffers go to one GPU or the other, and have state vary between them, say viewport or scissor state, which is what you would need to do to implement VRSLI type, one eye on one side of a buffer, the other eye on the other side of a buffer type of mapping. That's sort of like what we used to call, or maybe still do call, SFR, or split frame rendering, where it's one frame and GPUs do different parts of that frame. Okay, and if you want to learn more about Vulkan multi-GPU stuff, we have this cool, very detailed talk from Jeff Boltz, who's one of our main engineers working on Vulkan on YouTube. Okay, I'm going to talk briefly, which is perfect because we have 3 minutes, on optimization tools. Nsight, you guys all know Nsight probably. If you haven't checked it out, check it out. We've had it and have been improving it for a while. It supports, relevant to this talk, it supports all the VR SDKs. It gives you some amount of information about settings for the current HMD and how it's configured. It'll show you the two eyes. It'll show you the actual API state for the API state that you're sending through the OpenVR SDK, say, or the Oculus SDK. So it's fully VR aware. And that's true for sort of the traditional Nsight Visual Studio Edition that we've been shipping for a long time, and also the newly released that we just launched this week, Nsight Graphics, which is standalone tool that we have. So if you don't like doing your debugging, profiling inside of Visual Studio for your graphics application, we now have a separate standalone tool that gives you all the same feature-rich functionality, but not inside of Visual Studio. And then I want to talk quickly about FCAT VR, because I think this is something that probably most game developers don't know about, because it was initially sort of targeted more at reviewers. But I think anyone doing anything with a 3D application can use this tool. So FCAT was born out of a desire to basically increase the quality of benchmarking, because people traditionally just look at the frame rate and nothing else and just say, hey, the highest frame rate is the best. But we all know that highest frame rate is not necessarily the best experience, right? So we wanted a kind of a more feature-rich way to display what's really going on and quantify the user experience so that people could say, hey, the experience is better on this device or on this set of settings than it is on another, and do that accurately, more accurately than just something like Fraps would give you. So we built this thing called FCAT, and then we have this sort of follow-on to it called FCAT VR. And what it shows you is basically, the way it works is you capture your title running with like a hotkey that you press while you're running, similar to how Fraps works. And it collects data about sort of the performance characteristics of your game. It's very lightweight and easy to use, just like Fraps is. And then it has a visualizer that allows you to sort of dig into the data. What was the performance like? So this would be something you could use in QA or other places to just sort of get a handle on not only frame rate, but it reports all kinds of interesting things like dropped frames. So here we have a visualization. We have frame times for a bunch of different settings for the title Everest, which is the UE4 title. So you see sort of, this is different multi-resolution shading settings from off to aggressive. And then you can see here, you see the frame times. You see green means new frames, which is like normal rendering. And then yellow is synthesized frames, which is a frame that was synthesized using one of the warp techniques like asynchronous space warp. So it's technically a new frame, but it's not actually technically a new frame. So the frame rate is kind of not true in that case, right? And it's a synthesized frame is always worse than having a new frame. And so this highlights that there's actually a little bit of, there's some problem areas in this run through. Whatever happened here, they were synthesizing frames constantly in sort of the beginning of this run and towards the end. And then you can also visualize that this with the multi-resolution shading 3, which is the aggressive setting, you get almost no synthesized frames. So it smooths all that out. So it's, yes, the frame time is better, but the experience clearly is also better because you can now visualize what's really going on. And this is, I think, is a better proxy for the experience the user is actually experiencing. So yeah, so it'll show both dropped frames, synthesized frames, and warp misses, which is another concept where the warp actually wasn't able to complete in time, which is really uncomfortable for the user because then they use the previous warped results and all that stuff. So it's fully VR aware. Okay, so that's the talk, guys. This is sort of, again, just the overview. We have developer.nvidia.com/VR, which has a lot of information about various, all of the stuff we talked about today. And I think I can open it up to questions now. Yes, I think there's a mic, for questions, right? Thank you. They should go to the mic for questions, right, Alex? Yeah.
Hello, thank you so much for your talk. So my question is, in one of the versions where the video was, or the rendering was being warped, and then the picture was basically divided into 9 frames, why did the rendering choose to make the top frames shorter and the lower frame like bigger? Like they didn't look symmetrical. Is there a reason for that?
Yeah, let's look at it together, but it's not going to be symmetrical because the lenses are not symmetrical. So the optimal mapping is actually not a symmetrical one. So you're talking about in this video? Maybe?
No, not
No?
I think the one with the big room or the outdoor scene. Back some more, please.
Let's see. Let's go through the slide sorter together.
I think I forgot what it was called. Sorry. Yeah, this one.
This one?
Yeah. So
Yeah.
you notice the lower frame is not symmetrical with.
Yeah,
the
it's
top one.
that's a good question. I mean, this is all up to you, right? So, but I think in this case, it's because of the nature of the lens, because see, it's very asymmetrical itself, right? So this is actually like what the input to the lens wants to look like. So the distortion and the warp, let's see if I can go back, ends up being kind of a not symmetrical. And actually the 2 eyes are different too. So this is all depends on the actual optical characteristics of the lens. So this is, you can see it's not a symmetrical warp. So the ideal MRS set of parameters wouldn't necessarily be even either. You would want lower resolution in the bottom. But anyway, this is all flexible. It's up to you to set it. We have parameters that we've tuned that we think look good, which I think this slide reflects, but certainly our SDK reflects. And so it's going, and it's also going to vary from device to device. Like we have different settings for Rift versus Vive. Okay.
Thank you.
Sure.
I just wanted to follow up. I think that the bottom portion is larger because, for example, on the Vive, the screen extends further down than the center of the lens because it's very important to be able to see the ground below you. And they were discovering this in research early on. So that's why the screen extends so far.
That makes sense. Cool.
That part.
Thankful. Thank you.
Oh, also, I had a quick question about any of, like, in this case, does this use? I guess this bypasses the D3D stuff, but it doesn't use View ID, for example.
View ID?
View ID.
Oh, View ID. No, this is
View instancing.
The new View instancing stuff.
Yes.
TBD.
Okay.
Yeah. I mean, this demo certainly doesn't. This is a DX11 demo, but
right, okay.
But yeah, I think it could. A lot of this stuff could leverage that. I think we need to do some more experimentation with that. But yeah, that's a good point.
Maybe I'll talk to you afterwards.
Sure. Yeah.
Thanks.
Cool. Any other questions?